British officers watched the rifle fire, but nobody heard the shot. The bullet hit the target, yet the firing line stayed silent. The bolt moving sounded louder than the gun. The War Office immediately demanded an explanation, because this weapon broke nearly every rule of rifle design. It used pistol ammunition, it carried a massive built-in suppressor, and it was built for one purpose: to eliminate a target without revealing the shooter. This was the Lisle Carbine, Britain's quietest commando rifle of World War II. British officers gathered at a small firing range. A strange rifle rested quietly on a table. Engineer William Godfrey de Lisle prepared the demonstration. The War Office expected another suppressed experiment. Several similar experiments had already failed. Most suppressed rifles remained easily audible. Supersonic bullets produced unavoidable shockwaves. Conventional suppressors reduced blast, not ballistic crack. Whilst de Lisle claimed his rifle solved this problem, observers remained skeptical before the firing test. The rifle discharged toward a distant target. Officers heard almost nothing at the firing point. Several witnesses searched for the sound source. Many believed the weapon had malfunctioned. The bolt movement produced louder noise than the shot. That unusual result triggered immediate investigation. The weapon appeared built from Enfield components. However, internal engineering differed completely. De Lisle began explaining the technical approach. Extreme sound suppression required a different strategy. The design abandoned standard British rifle ammunition. Instead, it adopted the American .45 ACP cartridge. This cartridge normally traveled below the speed of sound. Subsonic velocity eliminated the ballistic shockwave. Suppressors could now focus on muzzle gases. Gas pressure created the remaining acoustic signature. Suppressing gas required exceptional expansion volume. Small suppressors failed during early experiments. Gas escaped violently through narrow chambers. Sound remained detectable across long distances. De Lisle enlarged the suppressor dramatically. The suppressor surrounded most of the barrel. It extended far beyond the muzzle. The suppressor diameter measured roughly 2 inches. Internal volume exceeded most contemporary designs. Large chambers slowed propellant gases gradually. A gradual expansion weakened the pressure wave. However, chamber volume alone proved insufficient. Gas velocity remained excessive during early trials. Engineers drilled multiple ports along the barrel. These ports vented gas into the suppressor early. Gas entered the chamber before bullet exit. Early venting reduced muzzle pressure dramatically. Porting also stabilized projectile velocity. Ammunition variation sometimes increased bullet speed. Porting prevented accidental supersonic transition. Engineers installed stacked metal baffle assemblies. Each baffle redirected gas into new chambers. Gases collided with metal surfaces repeatedly. Energy dissipated through turbulent expansion. Pressure decreased after each chamber transition. The final muzzle aperture remained extremely narrow. Minimal clearance preserved suppressor efficiency. However, narrow clearance created mechanical risks. Bullet alignment required extreme precision. Misalignment could damage the suppressor instantly. The machinists used alignment gauges during assembly. Every suppressor required perfect concentric alignment. Manufacturing tolerances became unusually strict. Suppressor tubes required deep precision boring. Internal surfaces required smooth machining finishes. Rough surfaces increased carbon fouling accumulation. Smooth surfaces improved maintenance reliability. The suppressor front cap remained removable. Maintenance crews inspected internal baffles regularly. Carbon deposits accumulated quickly during firing. Heavy fouling reduced suppressor internal volume. Reduced volume increased sound levels. Routine cleaning therefore became mandatory. Early prototypes experimented with rubber wipe suppressors. Rubber wipes deteriorated rapidly during testing. Fragments occasionally obstructed the bore. Engineers replaced wipes with metal baffle systems. Metal components tolerated heat and pressure. The rifle action required major modification. A Lee Enfield receiver formed the base structure. Original Enfield rifles used rimmed .303 cartridges. The .45 ACP cartridge remained rimless. Bolt faces required reshaping for the new case. Extractors required modified geometry. Extraction failures appeared during early trials. Polished chambers improved extraction reliability. Feeding introduced additional mechanical challenges. Standard Enfield magazines could not feed pistol cartridges. Engineers adopted modified M1911 pistol magazines. Magazine capacity ranged between 7 and 11 rounds. Magazine seating angle proved extremely sensitive. Incorrect alignment caused feeding stoppages. Feed ramps required reshaping and polishing. Pistol bullets possessed wide rounded noses. Wide noses amplified feeding errors significantly. Magazine spring tension required careful calibration. Weak springs slowed cartridge presentation. Strong springs increased bolt resistance. Repeated testing refined this balance gradually. The bolt action remained completely manual. Manual operation eliminated automatic mechanical noise. Self-loading rifles produced loud cycling sounds. The Lisle avoided that mechanical signature. Operators controlled bolt movement deliberately. Spent cases ejected only when the bolt cycled. Delayed ejection reduced metallic noise. The bolt retained Enfield rear locking lugs. Rear locking lugs tolerated moderate pressure safely. The .45 cartridge generated modest chamber pressure. But bolt thrust remained within Enfield safety margins. Trigger assemblies reused standard Enfield components. Trigger pull averaged approximately 6 pounds. The safety lever remained the Enfield design. Wood furniture originated from shortened Enfield stocks. Suppressor diameter required wider fore-end channels. Woodworkers removed large internal sections. Additional bedding stabilized metal alignment. Loose bedding risked suppressor misalignment. New sights required repositioning because of suppressor height. Front sights mounted near the suppressor cap. Rear sights simplified for short-range use. Sight graduations rarely exceeded 200 yards. Ballistic performance declined sharply beyond that distance. The .45 projectile lost velocity rapidly. Projectile drop increased dramatically after 100 yards. Operational range, therefore, remained intentionally limited. The weapon excelled during close engagements. Its mission involved silent elimination of sentries. Conventional rifles alerted entire defensive positions. Suppressed pistols lacked adequate range. The Lisle solved that tactical problem. Testing began during late 1942 development. Early demonstrations surprised British observers. Witnesses frequently heard only bullet impact. The bolt click became the loudest sound. Field trials confirmed this observation repeatedly. Acoustic measurements recorded extremely low signatures. Its testing occurred across different environments. Open terrain measured sound propagation distance. Woodlands evaluated echo and reflection behavior. Humidity influenced gas expansion slightly. Cold temperatures altered propellant burn characteristics. Engineers documented environmental performance carefully. Suppressor durability testing followed acoustic trials. Rapid firing produced internal heat stress. Baffle edges slowly eroded during repeated use. Engineers selected hardened steel alloys. These steel resisted erosion better than lighter metals. Weapon weight increased slightly because of this choice. Total weapon weight approached roughly 7 pounds. Most mass concentrated near the suppressor front. Forward. Balance improved recoil stability. Recoil impulse remained mild. Repeated firing increased suppressor fouling levels. Fouling gradually reduced expansion chamber volume. Reduced volume increased acoustic output slightly. Cleaning therefore remained essential maintenance procedure. Operational doctrine discouraged sustained rapid fire. The weapon served covert commando operations. Commandos required silent removal of guards. Large firefights exceeded the weapon's purpose. Manufacturing responsibility later transferred to Sterling Armaments. Sterling possessed precision machining capability. Production numbers remained extremely limited. Estimated totals rarely exceeded 200 carbines. Each suppressor required careful alignment inspection. Bore rods verified internal concentricity. Misaligned suppressors were discarded immediately. Repairing damaged baffles proved impractical. Production speed remained slower than standard rifles. Precision machining demanded skilled labor. Wartime factories lacked surplus machinists. Other weapons programs required the same workforce. Procurement officers restricted production numbers. Ammunition logistics created another complication. 45 ACP was not standard British infantry ammunition. Yet supply chains relied partly on American shipments. Special units maintained separate ammunition stocks. Separate logistics increased administrative burden. Despite these complications, operational demand remained. Commando units valued the weapon greatly. Raid reports praised its silent performance. Sentries could be eliminated without raising alarms. Nearby troops often failed to identify the shot. Night operations benefited from reduced muzzle flash. But the suppressor minimized visible firing signatures. Operators could remain concealed after firing. Few wartime firearms achieved comparable silence. The Lisle Carbine became historically distinctive. Every engineering decision prioritized extreme quietness. Range limitations resulted directly from this priority. Logistics complexity resulted from caliber selection. Manufacturing difficulty resulted from suppressor precision. Yet within its mission, the weapon excelled. Its extreme silence defined the entire design. The Lisle remained Britain's quietest commando rifle,